So you all just got some good practice with recursion. Now that you're a little bit more familiar with it, we are going to talk more about recursion. So a great way or reason to use recursion is because you can sort of divide and conquer. You can break up problems into these sub-problems that you realize you're doing a repetitive logic to, and utilize recursion of calling itself and doing that work for you. So if you find yourself that you have this big problem and you're breaking it out and you see a lot of repeating things, it might be a great case for recursion where you can just call it itself once instead of calling, doing that work over and over again. If we're trying to make like a return value that we're like adding to, it's a good way, similar to reduce, how we learned reduce this morning, how we have that sort of accumulator that we add to every iteration. Recursion is very similar, where we have the accumulator, which is the return value, and we're adding to it with every recursive call. So an example is we have, this is pseudocode, so I mean it's not going to run, but if we have this, if it's a number, then log it out. Else, for each index and val, if it's a number, log it out. Else, and we're just iterating through because maybe we have a super nested array and we don't know how nested it's going to be. It would be a nightmare to get it so that it would work for however nested we want it to be. Because we see all of these similarities, we can condense it into using recursion to take care of, like, if it's a number, log it out, else continue iterating, get one level deeper, and call it again. Because they perform the same action. So if you see the same action going over and over again. Recursion. So in this case, if it's an array, we're going to log array. Else, we're going to console log the element. So we know it's going to be an array, or in this case, a number. So if it's an array, we're going to call it recursively. Otherwise, we're going to log out the element and then call it on the next one. So we've logged out that first one, and then we remove it from the array and then call the function again. When we're console logging, it makes recursion sort of easy with the countdown. Countdown was straightforward because we had that console logging. Once we add return in there and we're trying to add up all the values with a return, that's when it starts, you have to start thinking about where you want that return value of the recursive call to go. Because in this case, it's just logging. This is a nice straightforward example. So our log function shows how you can use it to go as nested as you want, and you don't have to know ahead of time like the maximum number of nested arrays, because what if it's infinite? This way it will get all the way into each array. When dealing with any kind of nested complex data structure, an object that can have like an infinite number of objects nested within it, recursion is super helpful because then it will take care, if you have the right base cases, it will take care of going far into your data structures. And you don't need to know how deep you'll have to go, because sometimes you don't know. Sometimes, you know, it might be an array within an array, but maybe you'll have like 5 nested arrays the next time. So when should we use recursion? Because there's definitely some trade-offs with recursion. Sometimes the time complexity, it might take your machine to do an operation longer with recursion than it would iteratively, because you can't break out of it early the way you can with a for loop. Or also, sometimes it's not as easy to read and digest. And remember, one of the main goals of writing code is to write it clean so that anyone can read it and know what's going on. because you might not be there to explain it next time someone reads it. So sometimes recursion, although clever, can make it harder to read and understand what's going on in that method. But a lot of times, traversing nodes of complex data structures, so you have super nested objects, or you are branching and you want to iteratively go into branches of a data structure. Also, sorting in recursion is really well done. There's some really nice cases where recursion is like the best answer. Some functional programming languages use recursion instead of loops. So you won't have a for loop, you'll have, you'll call itself. Any questions on like when to use recursion, when not? Today, the answer is use recursion for workshops, but yeah. Yeah, great question. So a lot of times because of for loop, you can break out of it early. You can return and that'll like exit the function. That will decrease the time complexity. Also, sometimes recursion takes longer because you can't like skip elements and whatnot, and you'll go through each one. Or you have to perform more tasks to get to it. Normally it's about equal, but there are instances, and it's just something nice to keep in mind, because you're right. Like with these kinds of problems, 1 millisecond to like 2 milliseconds, not that big. But then once you are interviewing, being able to bring up time complexity as just a trade-off even is important. And then once you're on the job, because things can compoundly get more and more complex, keeping everything as effective as possible is important.
And like memory usage too, isn't it? Because it's calling the function like multiple times.
Exactly. It spins off a whole new instance of that function every time. And if your function's relatively small, that's not going to be that much different from like a for loop. But if you have a lot of other stuff going on in that function, that could increase the memory. And yeah, you don't want to create a program that uses up all the memory on your client's computer or like your phone. Like I hate apps that are using up like all my data and all my memory. You don't want that. So you want people to be like, yay, it only takes up this much memory.
So do you think you use like 50-50 in the real world, like recursion of for loops or while loops?
I actually don't do while or for loops that often. I do like mapping type iterations a lot. I would say I use recursion pretty rarely. When I do, I feel super smart. Like, oh, look at me. One of like our main selling points on our capstone, in my capstone group, was we made like a recursive like React component that created a new itself within the component, which we were bragged about in our presentation. So like it's one of those things that like if you find a really nice use case for it, where it fits and it's done well, it's great. And it's like,
Right. I can see how, like in real world, when say some engineer gets fired and you have to go back through their code and they had a lot of recursion, would be ultimately hard to debug what they were writing compared to like map.
Exactly. Yeah, exactly. Because mapping, it's a lot more straightforward of like, this is the input, this is the output. With recursion, it's like, how many times? But we do use it at my company sometimes to like unfurl certain data structures. Like we get from Outlook, it gives us these like crazy objects, and we join on all these different things to get all these different stats. And so we have to unfurl it all. But then we compact it. So it's like rare that we use recursion, but when we do, it's for something that's sort of tree-like in structure. Because then it's like smart about where it goes. And you don't have to be smart about it, because it does it for you. So as you saw probably in your examples today, logging something out, making the countdown recursion example, that was pretty straightforward because you're just console logging out the number. When you're returning from a function, figuring out where that return value should go on the next level down in your call stack that like called that function call, that can be a little bit more tricky. So really thinking about what's being returned, what do I want it to be like collected, accumulated with, is important. So yeah, remember when you call recursion, it pauses the like parent function call to start up the new one, and that's when like the call stack is made, and then it has to complete before the child function call has to complete before the parent function call can finish, and that happens when you return. And so knowing what's being returned when, super important. And you should always return. You should never have like a if something return this else and then you like log something out. If you're returning one place, always return. Okay, so we're going to do an example. I'm sure this will look familiar. Slightly different. I think you reversed an array. We're going to reverse a string. So I'm going to pseudocode it out. We'll see. Actually, I think we can do it while keeping it all a string. So we're first going to figure out the base case. So the base case will be when the string is just one letter. In that case, we'll want to return the string. The recursive case. So this will be if the string length is greater than 1. So if it's more than a letter, we're going to have to do some stuff. So we'll want to take the last letter and add it to the new string. And then we'll want to recursively call reverse with string minus the last letter. So eventually we'll get to a point where it's just one letter and we're just slicing off that last letter each time. So now that we have, and then we'll want to return the new string plus the recursive call. So now that we have it sort of mapped out, like what the goal is, we have cat. The goal is tack. Yeah. Let's do the base case. So if string.length is 1, we're going to return string. Cool. That was easy. Now for the recursive case. Else. Else, let's take the last one. So last letter, and that's going to be string, string.length minus 1. Remember, brackets work for strings as well. So this will grab the last letter because that's the last index. So we have the last letter. Then var returned result is going to be the recursive call reverse with the string minus the last letter. So string.length minus 1. Remember, slice works for strings too, and the first one is the index that's inclusive, and then the second argument is the last index that's exclusive. So if you say 5, it's not going to include that 5 letter, which will be the 6th letter. It's going to chop that off. So then we'll want to return last letter plus returned result. So we have a return here, we have a return here. Cool, we're returning both places. Let's run this. Cool, yay. So each time, let's console log string and see how each time we call a reverse, it's on a smaller chunk of the string. So each time we take the last letter off, we're adding it to the return value. But string is getting smaller and smaller until we get to the base case where we're just returning that letter C. What would happen if we did returned result plus last letter? Yeah, it's going to be the same.
Return.
Returned result. Because that's going to be on the call stack return string. This will be C plus last letter. So it's going to, if you're adding the last letter to the end, where you want to add it to the front. Cool. So then if we did hello, be hola. Cool. Any questions on sort of the breakdown, the base case?
Makes more sense when you did it in pseudocode.
Mm-hmm.
Like I like how, and that's what you're telling us in our examples is at the beginning to with the base case, just get it if it was one number, letter, array, whatever.
Yeah.
And then console log that to see it if it works there, and then go for your if and else statements.
Exactly, because if your base case is off, the whole thing's going to be wonky,
Right.
and getting that base case can sometimes be the hardest part of the recursive function. So yeah, going with, I'm not going to go with like a huge word here. I'm going to go with like, you know, I did 3 letters, but like I could have done like 1, made sure C is still C. Then I add a letter, make sure CA becomes AC. So like doing it small will work then on the big stuff, and you won't have to deal with like the complexity of like a word.
Right, and like we needed to, instead of we were trying to slice the whole thing, we just needed to slice like one thing at a time and see which direction it was going in, and then if we needed dot length and then -1 after that was I see how doing it in pseudocode like helps me understand it way more than just looking at it.
Definitely, especially with recursion. Defining in pseudocode the base case and the recursive case can like save you a whole lot of time. So when you're in the code, you get too stuck into the details, for me at least.
Right.
Cool, so in this case, I mean, they did it all in one line. I like to declare variables and then remove them later on. So we have hello. So we have that reverse hello call, which equals O plus reverse of hell. And then we call hell, that's L plus reverse of hell with 1 L. Hell with 1 L equals L plus reverse of he. He equals E plus reverse of H. H equals H. So we've gotten to the base case. Once we get to the base case, we can start returning and popping things off the call stack. So now this equals H, so that gets added here. Now it's EH, that gets added after the L. Sorry, it's a little bit off. The LEH gets added to the L. Now the LLEH gets added to the O, and now we have our end result, and then that gets popped off the call stack. So, writing a recursive function, figuring out what the base case or the break condition should be step number 1, because that's normally what the most simple input could be. The empty string, the empty array. What is the smallest thing that could be inputted into your function? 1 letter. when you're reversing it. Then define the recursive case, which is usually like the opposite of the base case. So if there's more than one letter, then do these actions. And then once you have 1 and 2 lined up, you can slowly, I like to do it step by step, log everything out, add the returns, make sure you're adding together what you should be adding, and returning what you should be returning. Any questions on recursion, especially after that workshop? Mm-hmm.
Every other time, a Fibonacci 6 or Fibonacci 9 or whatever, they will all then have access to that stored value and will only ever evaluate to one thing, right?
It depends on how you write it. Fibonacci is one of those problems that's a great problem for doing a lot, practicing recursion and all that. If you do it just the way that probably the solution code will have, you'll still be calculating Fibonacci 3 every single time you come up with it. There is something called memoization, which is a form of caching. So then you have some sort of object of key value pairs where the key is like 3 and the value will be that return value of Fibonacci 3. Then you'll only have to calculate Fibonacci 3 once. But that you need to do a little bit of work of making that object, passing it into the function every time you recursively call it. It's not hard. I can walk you through it, but yeah, your computer's not going to remember Fibonacci 3 is a return value. It's going to calculate it every time unless you explicitly tell it, like, oh, we've already done this. Yeah. But great question. So yeah, that could take up a whole lot of memory if you go to just like Fibonacci 10. It's calculating a whole lot.
So for that problem, it might make more sense to just use a for loop to make an array of all the numbers that point out to the one that you need, and that would use a lot less memory.
Yeah, you could do that for sure. You would still have to calculate like Fibonacci 5 to like Fibonacci. If you wanted to calculate Fibonacci 5, you'd have to calculate 4, 3, which
But
4.
4 and 3 stored in the array already? Like each time you iterate, you push it to the array, and then you just access the previous one.
Yeah, so if you added some logic in there to say like, oh, if this one's already in the array, use this instead of calculating it.
And you could just say it was like the array starts with 0, 1, and 1, and then you just keep adding to the array.
Yeah, but you would still have to calculate each one. Yes? Let's talk after. I think but yeah, there's definitely ways to do it where you don't have to be calculating each one every time. And in that case, with Fibonacci, sometimes recursion's not the most time-effective one, but it's a great practice of recursion because it lends itself well to repeating code. Cool. Okay, I'm going to